Okay, so chapter 18, chapter 18 review. 3 questions. First one, what are possible products of the following reaction? And are there different kinetic and thermodynamic products? We have a diene, and this is maybe for you a little bit unusual diene, where one double bond is what we call exocyclic, that means outside the ring, and the other one is endocyclic, inside the ring. But nonetheless, it is a diene system. So we should carry out our analysis as usual. So what are the carbocations that are formed, and what are the products? Here you have write-up. I posted PDFs, so you can read that, but let's look at equations. So this is addition of one equivalent of hydrogen bromide, so it's specified one equivalent of hydrogen bromide. So proton adds to the least substitute carbon, this carbon right here, and that gives allylic cation. Now there are 2 resonance structures of the allylic cation, and this one is tertiary allylic cation. So addition of proton to this double bond gives this tertiary allylic cation. That's actually pretty stable. Tertiary allylic is about as stable as carbocations get. There may be some more stable, but this is very stable. On the other hand, other resonance structure that's obtained by shift of this pi bond, the localization of this pi bond, is secondary allylic cation. That's less stable. So if you consider those 2 as 2 separate different cations, then more stable cation is going to be formed faster. And intermediate that is formed faster, of course, leads to formation of a kinetic product. So then when bromide anion nucleophile donates free electron pair to form bond with the cation, this is going to be kinetic product. And note that in kinetic product, double bond is di-substituted. We should compare that with the other alternative product. So when we consider less stable cation, and now reaction with bromide anion, that gives actually tri-substitute double bond. The more substitute double bond is, the more stable it is, which means that this is more stable product. So we have one product that is formed faster, and that's kinetic, and the other one that while it is formed slower, it is more stable, that's thermodynamic. So in this case, kinetic and thermodynamic products are different. Sometimes they are identical, the same compound is both kinetic and thermodynamic, but in this case they are different. So kinetic conditions, low temperature, short reaction times are going to favor kinetic reaction product. And thermodynamic conditions, that means higher temperature and longer reaction times, conditions that allow for equilibration, will favor formation of thermodynamic product. Next, second question, consider each compound A and compound B, reactions of compound A and compound B with one equivalent of hydrogen chloride. So 2 separate compounds. What is the product of each reaction? And which of the 2 compounds reacts at a faster rate? So first we have to consider them individually. So compound A reacting with hydrogen chloride. So when you consider compound A, there are 2 double bonds, and it is a hydrocarbon. So the only effects are inductive effects of hydrocarbon substituents, and those are positive inductive effects, donation of electron density through sigma bonds. Effect is relatively mild, but nonetheless it's there, and more substitute double bond is more reactive because it's better electron pair donor, better nucleophile, because of the donation of the electron density from alkyl substituent. In this case, alkyl substituent is cyclohexyl group. So this more substitute double bond is going to be more reactive, and upon reaction with electrophile, it generates tertiary carbocation. That's another way to look at it. It's better electron pair donor, but also it generates more stable carbocation, more stable intermediate. And then upon reaction with fluoride anion, this is the product. In case of diene B, we have oxygen as substituent on one of the 2 double bonds. And so that double bond with oxygen substituent is more reactive, because of the electron donation by oxygen atom to resonance effect. So that's positive resonance effect plus R effect of oxygen. And resonance effect is much stronger than that of alkyl group. So right away we can tell that compound B reacts at a faster rate because electronic effect is stronger. It's more pronounced. So compound B will react faster than compound A. If we were to mix compound A and B together and add just enough hydrogen bromide to react with only one of the 4 double bonds, only this double bond would react, this double bond of compound B, or at least predominantly would react. Now, when it comes to the actual outcome of the reaction, as a result of electron donation from oxygen, is this terminal carbon, end carbon, one away from oxygen, that carries partial negative charge and excess electron density. So that's where proton bonds to. And this is the intermediate cation. There are actually 2 resonance structures. This is lower energy, which is stabilized by oxygen. That cation reacts with chloride and ion to give the final product. So that's the question 2. And finally, question 3 is a little bit longer. What are products of the following reactions, including stereo and regiochemistry of each product? So you have 3 reactions here. And at first glance to some of you, this may appear a little bit puzzling because you may not recognize what are these reactions and what is going on here. If you looked at the answers, you probably know already. Okay, so in this case, it's important to recognize that compound on the left is diene, and one on the right is double bond with electron withdrawing group, dienophile. And so diene and dienophile react in a Diels-Alder reaction. So that's Diels-Alder reaction. Frequently, students don't recognize this as Diels-Alder reaction because we don't write it that way. We usually, for convenience, represent them kind of vertically, like this, to help students identify the product. Drawback of it is that when reactants are represented differently, students often fail to recognize that this is Diels-Alder reaction. So make sure that you can recognize it even if reactants are represented differently. And then if you recognize it as Diels-Alder reaction, it's a good idea to redraw the reactants so that you can draw correct products. So you redraw reactants so that double bonds are essentially vertical. And make sure that you retain stereochemistry of each double bond. So this is trans double bond. You see it's trans in the starting material. You see double bond is trans in the starting material. And that's the only double bond that exhibits any stereochemistry. And so it has to be trans in this vertical representation. Now, for the other reactant, substituent should be drawn in such a way that it points towards the dienophile so that in the final product it ends up under these double bonds. That's actually really called endoposition. And you may recall endo rule that these other reactions occur in such a way that substituent ends up in endoposition. And so so technically it's endoposition, but you draw it in such a way that at the end it appears kind of under the plane of the ring. So to figure out what is the product, you draw the transition state. You draw transition state by connecting carbons of diene and dienophile that will form new sigma bonds. I indicate them here with dashed bonds. Unfortunately, here substituent interferes a little bit, but this is the dashed bond. See, going from this carbon attached to oxygen, carbon 1, to carbon attached to nitrile group. And this is the other one. I represented this nitrile group as carbon-nitrogen triple bond to show you why there is endo rule. Because this pi electron cloud interacts with pi electrons of the diene, and that stabilizes the transition state. And that's why we have this endostereochemistry. That's why substituent ends up below the plane of the ring. For steric reasons, actually it should be on the outside. So sterically this would be less stable. And now to figure out what is stereochemistry. First, of course, you should first, of course, you should actually consider regiochemistry, not stereochemistry. So when considering regiochemistry, dienophile could be oriented like this, with substituent pointing up, which means that in the final product, two substituents would be 1,2 to each other, next to each other, or ortho. Or it could be upside down, where nitrile group or substituent points down. Then two substituents would be 1,3 or meta to each other. Recall ortho-para rule, substituents are always 1,2 or ortho to each other. So this is correct orientation. You can do both and see what each orientation gives you, and then, of course, ortho or para are correct. So in this case, it's going to be ortho products. They're going to be next to each other. But the question is now that you know regiochemistry, it's 1,2 or ortho. By the way, ortho, of course, only applies to aromatic compounds, and this is not aromatic, but we still call it ortho-para rule. Strictly, it's 1,2 relative relationship. So now looking at stereochemistry, you see this new bond that you're drawing here that is dashed. So two hydrogens are both above the plane of that bond. You can see clearly if this is bond, you can easily tell this is up, this is down. This is up, this is down. This is all on one side and this two on the other. So if two hydrogens are up, then both substituents are down. And you show them as down, and that's correct stereochemistry. So the product is cis. And then we apply the same procedure on the next compound. Difference between this compound and the previous one is double bond is cis. So you should represent it as cis when you redraw reactants in these vertical orientations. And then again, you draw a transition state in such a way that substituent is under the diene system or points down. Show newly formed bonds. And now you can tell that this methoxy group is up, hydrogen down, relative to this new bond that is being formed. This hydrogen is up, nitrile down. So methoxy up, nitrile down. We can show hydrogens, but they clutter the drawing and don't add any information. So we usually only show substituents. And so that's correct. Regiochemistry, it's 1,2 or ortho, and stereochemistry is trans. And then here's third reaction. In third reaction, you should recognize that substituents can no longer end up in 1,2 relationship to each other. So you should redraw them in such a way that they end up in 1,4, since 1,3 is not possible. 1,4 or para. And in this case, that's the only trick. Just make sure that substituents are 1,4 to each other. Because in this case, stereochemistry is not possible. We don't have cis-trans stereochemistry. This atom, carbon atom here, that is attached to nitro group, is chirality center. And so this compound does have two enantiomers. But both are produced in the course of reaction in equal amount because we don't have any chiral induction. There is no reason why one enantiomer should be produced in larger amount than the other, because there is nothing to induce chirality. For example, neither of the products is chiral. If this substituent, instead of methyl group, if we had something chiral here, then maybe there would be some chiral induction and there would be preference for one enantiomer. Or if we added some chiral catalyst or used chiral solvent or something like that, then we could have preferentially one enantiomer. But in any case, at this level, introductory organic chemistry course, you wouldn't be able actually to do proper analysis of something like that. So if it's only a chirality center, you don't worry about stereochemistry because there is no preference for one enantiomer over the other. But if it's cis-trans, as in previous two examples, you need to know how to determine whether the product is cis or trans. And this completes this relatively brief review of chapter 18. So the most important and a little bit complex. So this is actually a combination of most important aspects of chapter 18 and also a little bit more complex concepts of chapter 18.